Hello, fellow students of chemistry. Today, we'll be talking about the nitty-gritty stuff that makes up chemistry when you look at it. That being said, the first thing is that we're talking about chemistry. What's that big, weird shaped thing with a bunch of little squares in it? You know, the thing that you have on the wall in your chemistry classroom. Periodic table, that's what we call it. Okay, so the periodic table. And the periodic table has over 100 wonderful elements, and these elements make up everything. So they're going to be your building blocks of nature, every biological organism, every, piece of the graphite of the pencil that you're writing on your test, everything. That being said, chemistry is about the atoms, but it's also about what they make up, and that's going to be compounds. So when you have atoms getting together, they're going to form compounds. In certain circumstances, when they're covalently bonded, they're going to form molecules. When they're ionically bonded, they're going to form formula units, and then these giant cool crystals. That being said, you can describe these compounds by the symbols of the elements that make them up. For example, Cr2O7 is going to be the formula Cr2O4. Cr2O4 would be the symbol for chromate, which would be an ion. Or you could say H2O, the simple formula for water. And that's all you really needed to know for this. And you guys are probably very familiar with these formulas already. You've done all the good ionic bonding stuff. You've seen covalent formulas. You're like, I got this. So we're going to move on from there. Chemical equations then use these formulas, once you have them, to essentially tell you what's happening in a chemical reaction without going into depth saying, okay, what we have here, we have blank reacting with blank to form blank, or blank decomposing to form blank and blank. So along the lines of the basic chemical reactions, for example, you have your decomposition, your synthesis, your single replacement, your double replacement, your combustion, and your neutralization reactions. All these wonderful reactions that you'll be looking at a little bit later in our review of this course. Just remember for right now, for reaction, on your left, you're going to have your reactants. That's what's going in. It's like in a function. That's going to be your x heading into the fx. And on the right, on the other side, my left would be here, this is your reactants. Your right would be here, that's going to be your products, what's coming out of your reaction. That's going to be your f of x. And so, for example, a basic reaction, if you're forming water, you would have H2, because hydrogen's diatomic, H2 plus O2 would equal H2O. But wait a second, that's odd, because you see H2 plus O2, you have an extra O left over. That's right, fellow students. And once you have that extra O left over, you notice, something's wrong with this equation. This is a skeleton equation. It has the basic forms of whatever elements you're putting into it or whatever compounds you're putting into it, but it doesn't yet have the coefficients that would make it balanced. Then you have to balance the equation. So now you have that H2 and that O2, and that's going to form H2O. However, to balance, you add the coefficients to make this correct. For example, for here you would be adding the coefficient of 2 in front of H2. So 2H2 plus O2 equals 2H2O. And when you notice this, you're going to see 4 H's, so 4 hydrogen atoms on the left side of the equation, 2 oxygen atoms on the left side of the equation, and then on the other side, 2 H2O's. And that's going to be 2 oxygens, and then 2 H2s, so 4 hydrogens. Boom, it's balanced. And we'll talk a little bit more about the nitty-gritty of how to balance these equations later. For now, we're going to move on to mixtures. What happens when you didn't necessarily have enough energy, or the stuff just wasn't right for there to be a chemical reaction? So instead of having it be, say, H2O, you simply have a mixture of H2 and O2. A mixture is when chemicals combine without any chemical interaction. That's purely physical properties. So you're saying, we've got all these atoms or all these compounds mixed in together, but the atoms in compounds, if separated out, will still form the same component parts. For example, if you were to combine water and salt, it dissolve salt in water. If you were to boil off the water, the salt's still there, and if you collected the water that you boiled, the water's still chemically the same. It's just been physically mixed. That being said, these components have no links chemically, and instead they just coexist in the same realm because they're either suspended or they're actually mixed in smoothly, like in the case of salt, where it's actually dissolved in the water. We see two types of mixtures. Homogeneous, and if you notice, homo, which is the Latin or Greek root for same, homogeneous mixtures are the same throughout. So, say if I have this mixture, and that's going to be, again, a mixture of water and salt. I take it, and I take 1 teaspoon of this mixture, and I look at it, and then I separate it out into a dozen teaspoons. All of these will be the exact same, and I can separate it out again, and again, and again, until I get to the molecular level before you notice the water and the salt are separated. All that means that the distribution of salt throughout the water is going to be even. On the other hand, a heterogeneous, and hetero meaning different, heterogeneous mixture is, say, a mixture of water and flour. What happens when you mix water and flour? Well, at first, it'll just be this cloudy solution. You won't be able to really tell there's a higher concentration of flour anywhere because it's currently suspended in the water. However, as the flour settles over time, you're going to find the flour heads to the bottom because it doesn't remain dissolved in the water, and instead its weight, which is greater than that of the water, will bring it down to the bottom of the mixture. So if you were to take this and separate it out into teaspoons, at the very top there'd be a lot of water and not very much flour because most of the flour will have settled down. However, at the bottom you can see a big old clump of gooey wet flour, but not very much water because the flour's taken up all that space. And that's all it really is. This homogeneous is an even mixture where everything's spread smoothly throughout, and a heterogeneous mixture is one where it's not evenly mixed. In a homogeneous mixture, it can either be a colloid, which is when you've got particles suspended, for example, in milk, and they're never going to fall, so it's still heterogeneous, it's still homogeneous, because it's still the same throughout. However, these particles are not dissolved, so you can still see that when you're looking at it through the light, it's going to be opaque. Or you can have one where it's fully dissolved, in the case of salt water, where you're not going to be able to notice a difference, and you can look through it, and it'll still look just like normal water. And that's just a matter of how evenly the molecules are getting dissolved throughout it. With a colloid, you have larger molecules that don't necessarily get dissolved, but get suspended. With a mixture where they're dissolved, they're actually down to the molecular level having been separated, and at this point, you would have to use some sort of state change typically, or highly advanced filter to separate them out. Next up, we have states of matter. So, states of matter harken back to the good old days, and I'm sure you guys remember them. We're going to be talking first about the main three, and we'll bring up the other two, your plasma and Bose-Einstein condensate, later. And with your main three states of matter, which will be the ones that you'll deal with 99.9% of the time in the chemistry classroom, you'll see that gas, liquid, and solid. And each of them have their own special properties. For with a solid, it's going to be closely packed because with low energy, the molecules or the compounds within that solid aren't going to have enough movement. They're not going to have enough energy to break free of each other. So they're going to get bonded together by strong intermolecular forces and stick together like glue. And a solid can obviously be anything from wood to a stone to anything, well, solid. That's pretty straightforward. It's going to have a fixed shape because, of course, a solid isn't going to start falling apart, at which point it's going to be a liquid. Because, obviously, you have a solid, because they're locked in together, because of the strong intermolecular forces, the molecules or the compounds aren't going to be able to move very much in relation to each other. So if I have this box, it's not going to suddenly go, no, it's just going to stay a box. No matter what I do to it, it's still going to be a box. I can set it down, I can pick it up, I can move it over here. No matter what, it'll be a box. Boom. Next up, we have liquids. Liquids are going to be more spaced out. And that being said, however, the liquid version of anything from a solid to a liquid, you're going to see a lot more energy being inputted. And this energy is going to allow the bonds, the intermolecular forces between each compound, to be a lot weaker. So, for example, the liquid form of water, the bonds between that H2O is going to be a lot weaker than in the solid form, so that they can slide around each other easily. So when you have this molecule, instead of being boop, stuck together, they can go shloop, sliding around. That being said, there will still be intermolecular forces, which means that most liquids are going to display some sort of connection to each other. So if water, obviously you see that it'll form a meniscus when put in a glass, or any other, when, say, you put it on the table, it's going to end up sticking to its covers because of its bonds, it's these intermolecular forces. Some liquids will have weaker intermolecular forces, some will have stronger, but all of them are still going to have some intermolecular forces acting on them. That being said, even though liquids can slide around, liquids still have a fixed volume. And that's why, say, something like a hydraulic system might work. It's because water, no matter what it's in, 100 milliliters of water will still be 100 milliliters of water. So it's not compressible. That being said, under highly extreme pressure, the compression can cause it to revert back into solid form, but under normal levels of pressure, it's going to end up staying liquid. It's also not going to expand, so if I have 100 milliliters of water, it's not going to suddenly become 110 milliliters, because the molecules are still connected by those intermolecular molecular forces, and they're still going to be together. Finally up, we have gases. Gases are when the energy levels get so high that you basically start to have a total party. And at this point, the atoms, or the molecules, or compounds, whatever you're dealing with, just start flying around wherever. They don't care. They've got no attraction left because they've reached such a high energy level. There's woo, 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 woo. So, what does that mean? It means that gases are compressible because they're not next to each other. When you have these molecules, say the gas, hydrogen, your H2 and H2 molecules, your diatomic molecules, they're not going to be next to each other because they've broken free of each other. So they're going to be flying around everywhere, which means that you can compress them so that they take up less space. That means that they're not going to have a fixed area, they're not going to have a fixed shape because they can fly up and then they're going to form into the shape of whatever container they're being held in. So you can get hydrogen gas and you can put it in this little can, but you can also put it in a big old box and it's just simply going to spread out to fill the space that it's placed in. That being said, it's also going to have no volume, which means you can compress it easily. Unlike a liquid with a hydraulic system where it's not going to be compressible, in a pneumatic system where you're using gases, it's going to be very compressible. Think about, for example, if you've ever gone camping and you have a camping mat that you're sleeping on, and it's filled up with air. Why is it comfy? Because it doesn't compress. So that air that you're sitting on, which is going to be held in, is going to be a constant amount of air because no air is escaping from the sleeping pad. However, it's going to be compressible based on your weight, and that's going to allow you to sleep comfortably. Versus if you were on a liquid mat, it might be less comfortable because with water, it's not going to have any compressibility. And if you had no mat at all and were just on the solid ground, not comfortable at all because no compressibility, and it wouldn't be able to morph its shape to meet the shape of your body. Because obviously a water bread is still pretty comfortable, albeit taking you back to the 80s. With that said, that pretty much covers it for gases, and we will come back to our in further episodes and possibly discuss a little bit about plasma and Bose-Einstein condensate. For now, all you really need to know about them is they're not that important, and they don't really happen that often. So, one last thing with changes of state is the idea of kinetic theory. This idea that energy governs the state that these compounds or molecules are held in. So, low energy, you're going to be a solid, and you're going to be held together. And as energy levels increases, you're going to get up to this melting point. Once you reach this melting point, the temperature, which is the amount of energy being inputted, is going to remain stable. Because as you input more energy, it's going to simply absorb that energy until the entirety of whatever you're trying to melt melts. So you end up getting this plateau. then it's going to do the same thing. Energy is going to increase, and then the temperature will increase as it moves from a liquid to a gas, and finally you'll hit your boiling point. Once you hit your boiling point again, the liquid's temperature will plateau, which is why water, when it's boiling, it will stay at 100 degrees Celsius. You can't get it to boil any hotter unless, of course, you go up and you increase your pressure. But at a standard pressure, at STP, standard temperature and pressure, standard pressure, not STP, because it's going to be 100 degrees. At 100 degrees, it will be boiling, and it'll stay at 100 degrees no matter how much energy you put in until the entirety of the water is boiled, at which point it's going to become a gas. And then once you hit gas, you could input essentially any amount of heat, and it's going to continue absorbing the heat until finally, at some point, it's going to start to become a plasma. And that about covers it. Remember, liquids and gases are both fluid, so they will diffuse. Their diffusion will be governed, when it comes to liquids, by the amount of intermolecular forces there are, which is why water will only diffuse so much before it forms up into, the little spheres of water on your floor. Which is a good thing when you think about it, because if water were to diffuse infinitely, you would get this tiny microscopic sheen of water covering your entire floor, and that'd be really hard to clean up a spill. But gases, not the same. Gas will diffuse infinitely until it reaches the edge of whatever's holding it, because there's no intermolecular forces to hold that gas together. Which is why I say, if you have carbon monoxide being produced in your basement, and your basement's closed off, that carbon monoxide will fill up your entire basement, and anywhere in the basement you go, you'll be able to get carbon monoxide poisoning. Woo! Don't get carbon monoxide poisoning. Finally, remember with these states, when you're doing your equations, and you want to write a fancy skeleton equation or a fancy balanced chemical equation, you can write your states, which would be solid, liquid, gas, or aqueous. Solid, liquid, gas, or aqueous. Dude, aqueous isn't a state. Hold on. All aqueous means is simply dissolved in water. Because so many chemical reactions occur with compounds that are dissolved in water, we've created aqueous, and that stays with the rest of the states because it's so important. All that means, like I said, just dissolved in water. Like salt dissolved in water would be the aqueous form of sodium chloride. Boom. And that's about it. So use solid to indicate it's solid, liquid to indicate it's liquid, gas to indicate it's gas. It's just one letter added on, and it adds for a lot of clarity. Because if somebody's trying to follow your chemical equation, and say you're trying to create salt, and you're saying, hey man, what you need to do is you need to react sodium with chlorine. Well, reacting sodium with chlorine is going to be kind of hard if you have them in their solid states, versus try to react them in their liquid states, or even their gaseous states. So it helps people who are then trying to follow your equations, or your chemical reaction formulas, to then know what they need to do. Remember with your states, that when they change states, they have special names. Most of them are going to be pretty easy because, well, you've heard them a lot. For example, solid to liquid, it's just melting. And then liquid to gas is going to be boiling. However, do you know what gas to liquid is? I'm going to check right now because I don't remember. It's going to be condensing. Going from a liquid to a gas can also be evaporation, because boiling is when you reach that critical temperature that requires it to go off. However, evaporation is the natural level of energy, because in any substance, you're going to have a higher level of energy at your very edge. It's the natural level of energy for particles to just fling off of that liquid and join the gas. So keep that in mind that boiling, say for water, boiling at 100 degrees Celsius, that's when it's all reaching that temperature and it's all starting to fly off and become a gas, versus evaporation, which is when you just have maybe 20 degrees Celsius, but a little bit of your water is going to be slowly flying away, just those surface particles. Next, when you're looking at going from a solid to a gas, which is a pretty big jump, and this is when you have no liquid phase in between. A good example of this, if I can remember one, would be, forget it, I don't remember a good example of going from a solid to a gas, but that'd be sublimation and deposition. So sublimation is poof, you're basically getting vaporized. You go from that solid, and now it's gas. Deposition, just remember, depose is you're going down, you're no longer king, and you're going to be knocked off of your state. So you're all up, you're gas, you're partying, and now you've been deposed, deposition, and it goes all the way back to a solid.
Well, Kyle, I think I can save you here, because a nice example of sublimation is, if you ever recall getting a new car, smelling that new car smell, that's an example of sublimation in your daily life. These chemicals that are in the car that used to be solid are subliming. Yes, that's what it's called, subliming, like the band from the 90s. And that creates gases, very aromatic gases, that you then inhale and can now smell as a new car smell. Don't smell too much of it, you could die.
Have fun. Have fun smelling that new car smell. And just like carbon monoxide, don't hang around it too much, like Lucas said. Finally, remember, from going from a solid to a liquid, probably not going to remember these. It's going to either be melting or freezing. And that about covers it. We've got one last thing to go over here. Evaporation only occurs on the surface. Just remember, you can't have the middle of something evaporating because it just doesn't work. Like, think about if you had a cup of water. If it was evaporating from the bottom of the water up, it's not having actual contact with the air. Just like in a chemical reaction, you can't have chemicals that are reacting that don't have physical contact with each other. Evaporation can't occur because that's when you're being in contact with the air and the pressure being low enough for particles to fling off on their own. Versus boiling, which can't occur anywhere. Because if you've ever seen a pot boiling, you'll know these bubbles are coming up from the bottom. Because they're literally turning to gas within the liquid. Just keep that in mind as the difference between gas and liquid, between boiling and evaporation, going from gas to liquid. And finally, there's this wonderful graph, which is the graph of your state changes. All you really need to know is it's this wonderful stepping graph, because at first, your energy's increasing, or your temperature's increasing of your substance, as you're pumping in more and more energy, boom! So you had a solid, and now you start to melt. Now you're melting, okay? But because while you're melting, while you're going through a change of state, your temperature isn't going to change. You're going to continue putting in energy until all of that substance has melted. Now you're at a liquid. You go up, temperature still increasing as energy increases. Then you're going to again hit this point where your temperature levels off and your energy is going to continue to increase, and that's why your liquid's boiling. And while it's boiling, it's going to stay there until all of your liquid's gone. Now you're at gas, and it'll continue increasing ad infinitum, and then you're done. You've got your changes of state, you've got your stoichiometric relationships, you've got your skeleton equations, and you know that everything's made up of atoms. Nicely done. We'll see you in the next chemistry video.